Understand the state of the substance at 400 Kelvin. The problem states that when the temperature of CH3OH is increased to 400 Kelvin, all of the liquid vaporizes. This is a crucial observation. Because there is no liquid remaining, the system is no longer in a liquid-vapor phase equilibrium. Instead, it is a single-phase gas system governed solely by the gas laws. Relate the mass of the sample to the number of moles of gas. The number of moles of a substance, N, is calculated by dividing its mass, M, by its molar mass, M. N equals M over M because the identity of the chemical, CH3OH, does not change. Its molar mass is constant. Therefore, repeating the experiment with half the mass means that the container now contains exactly half the number of moles of gaseous methanol. N new equals 0.5 times N original. Apply the ideal gas law to the constant volume system. The relationship between pressure, volume, temperature, and moles of a gas is given by the ideal gas equation. PV equals nRT, therefore, P equals N times RT over V. The volume of the rigid vessel is constant. V equals 2.0 liters. The final temperature is constant. T equals 400 Kelvin. The gas constant, R, is constant. Since the term RT over V is entirely constant, the pressure of the gas is directly proportional to the number of moles of gas present. P is proportional to N. Calculate the new pressure. Because all of the methanol will also completely vaporize under these conditions. With even less mass, there is no liquid remaining to limit the pressure. We can directly scale the pressure based on the proportional decrease in moles. P new equals 0.5 times P original. P new equals 0.5 times 0.30 atmospheres equals 0.15 atmospheres. This matches option A. The correct answer is option A, 0.15 atmospheres.